Again, I'm Mike Stay. I'm the CTO and co-founder of Pyrofex Corporation. When we founded Pyrofex, we weren't thinking at all about cryptocurrency. We were going to focus on really writing an operating system for data centers. And we wanted to make it possible to deploy software in any environment and then have it link in the appropriate algorithms for use in that environment. So sorting on your laptop, maybe use quicksort, but in a data center you want the distributed merge sort of thing. But then we got the opportunity to do some consulting for Archain and got introduced to the wonderful world that is cryptocurrency, the volatility, the Wild West, all of the craziness that goes on there. And we started looking around at the systems that cryptocurrency companies and groups were deploying and said, this is all wrong. This is not the way you build a high-performance network. And so we went back and, once our contract with Archain ended, we looked over what we thought a cryptocurrency network ought to look like and came up with CDelta. So it's proof of stake and bandwidth. In order to not consume the energy output of the nation of Ireland to get 15 transactions a second, you've got to do something else. So proof of stake was originally proposed where if the miner has some of the currency, they're not going to want to mess up the network. But it turned out that there were long-range attacks, that once they were done using their key, they could take all of the they could go and form an alternate reality network. They could fork it themselves and use their key to deceive people that were joining the network in the future. So what we use is bonded proof of stake. That gets around that problem, that you put up a big chunk of money, and rather than in proof of work preventing people from doing things wrong, you detect misbehavior after the fact and slash their bond. For bandwidth, you've got to be able to keep up with the network if you want to have a really high performance network. You can't have somebody sitting behind a cable modem in Singapore if you want to have high performance in DC, right? So the participants here need to have enough bandwidth to keep up with all of the blocks that are flowing through. So those two things, the stake and the bandwidth, are the basis of the motivations that keep the miners, or validators as we call them, in line. The other thing that we noticed was that 98% of the contracts on Ethereum are ERC20 tokens, right? It's just about exchanging money at this point is the major use of it. So we figured we would get that right before trying smart contracts. Now we have designed our system so that we will eventually be able to do smart contracts, and I've got a slide about that towards the end. But first we're going to do money. The next is that it's decentralized and open. Now there are two aspects to decentralization. One is the decentralization of the mining network, and the other is the decentralization, the openness of allowing others to come in. So you need to have enough players so that the SEC isn't going to come down and say you're a security, so it can be freely exchanged on exchanges. But you also need it to be open so that other people can participate and reap the rewards of this thing. So if you don't have enough money up front to stake, but you can deploy your hardware, all of the work that your computer does goes towards your stake until you're fully staked, and then you can vote on the things. So in the meantime, you can confirm blocks that are done, but you don't get to vote on conflicts. All nodes are producing blocks all the time. In many, even proof-of-stake networks, there'll be some kind of leader election or round robin, and one guy gets to say what the next block is. In our system, everyone is producing blocks all the time. It gives us an enormous number of transactions per second. We have proofs about the structure of our directed acyclic graph of blocks that let us get true finalization within about 2 minutes. That means that you're never going to get 51% attacks that roll back hundreds of blocks. The only things that could possibly be rolled back are the things that haven't finalized within the last few minutes. Initial deployment, 105 validators. We're looking at about 83 transactions per second per validator. So we'll be running at about 8,000 or 9,000 transactions a second. And given the bandwidth requirements that we're putting up front, 1 gigabit line, a third of which we're using for blocks, that scales up to about 2,500 validators and around 200,000 transactions per second. So we're looking at approximately 4 orders of magnitude faster than the most popular blockchains. And it's all written in Haskell. So Nakamoto consensus. It never truly finalizes. Ethereum Classic, Bitcoin Cash, both recently, within the last month, had 51% attacks. With Ethereum Classic, they rolled back hundreds of blocks, simply because they didn't have enough computing power to withstand a concerted attack. Bitcoin Cash, there was an attack, and then the miners got together and mounted a 51% attack against the attacker to try to secure their system. But they weren't mining on Bitcoin Cash normally. They just got together a whole bunch of computers in order to defend against these other computers. It's rather like the Highlander movie. There can be only one. For a proof-of-work system to be secure, it has to have 51% of all the world's computing power forever to remain secure. As soon as it doesn't, or unless you add checkpoints, in which case you're trusting the developers rather than trusting the network, that's just the nature of proof-of-work system. And it is slow. It gets, Bitcoin gets about 7 transactions a second, Ethereum around 15. This paper here on scaling decentralized blockchains, I'm going to put up some QR codes if anybody wants to look these up quickly. Demonstrate that the best that Bitcoin can do is a block size of around 4 megabytes. And this was in 2016, before the network had grown to the size it is today. That corresponds to about 27 transactions a second. If you try to do more than that, if you try to go to the Bitcoin Cash 8 megabyte size, essentially the network partitions, China wins. US can't keep up with all of the blocks being produced in China, so they never get any mining rewards. So these were our design principles. First, make the system fast in the best case. We'll look and see that when nobody is producing conflicting transactions, all you need is attestation. You don't need consensus. There's only one value you could possibly choose when there's no conflicts. So first we build an attestation network. Second, only punish the misbehaving parties. So for punishing validators, we have the proof of stake and slashing and ejection for underperformance. And for punishing a client of the network who is attempting to double spend, their transactions slow down, but no one else's do. Third, only enforce as much order as necessary. If Alice pays Bob and Bob uses that money to pay Carol, of course those have to be in order. But if Alice pays Bob and Carol pays Dave, there's no necessary correlation or ordering between those. So we use a directed acyclic graph rather than a linear chain. And fourth, once we have a good consensus algorithm, we design an accounting system that doesn't slow it down. Even with Casanova, our consensus algorithm running, if we had Ethereum's transaction model, all of those transactions can potentially conflict with each other, and so we necessarily need to put a total order on the whole thing if we adopt their model. So we've chosen a somewhat different model that doesn't screw up the speed. This is the paper by Kyle Butt, Derek Sorensen, and myself. Kyle Butt is our senior staff engineer. This algorithm is largely his work. Derek and I helped with discussions, and he graciously allowed us to be co-authors on this. But I encourage you to read this. In this paper, we prove that Casanova is live, that it's safe, and constructed in the way that I'm going to talk about in this talk. So the first thing we do, as I mentioned, is talk about an attestation network. So when there are no cheating parties, then all we have to do is record the fact that a transaction occurred, not decide which one occurred. So in our system, blocks can refer to multiple parents, and in general they refer to the latest block that they've seen from each of the other validators. We decided to do 1 megabyte blocks issued once a minute. So if you get a block from somebody else that's sooner than you expected to get one, that it's got a timestamp that's ahead of your clock, you just hang on to it until your clock passes that timestamp and then acknowledge that you've received it. At 1 megabyte blocks, our transactions are roughly 200 bytes. The simplest transaction works out to be about 180 when Alice pays Bob. That gives us around 5,000 transactions per block. And each validator is producing 1 block a minute. That works out to 83 transactions per second per validator. If we assume a gigabit per second connection, use a third of it for downloading blocks for other validators, that works out to 208,000 transactions per second. So Visa peak speeds of 24,000 per second. This means that we can, fully deployed, we'd be able to handle several Visa-size networks, Visa, MasterCard, et cetera, and banking system-size transaction volumes. The next thing we do is look at how to resolve conflicts when they occur. So when a conflict comes in, if Alice goes to this validator and says, I want to use check number 1 to pay Bob, and then goes to a different validator on the same network at the same time and says, I want to use check number 1 to pay Carol, then when they find out about these conflicting transactions, the validators attest to the fact that they've seen it, and then start a side protocol for resolving which of those two the network is going to accept as valid. So once those voting rounds that happen in the side protocol piggyback on the blocks that are already being sent. So there's a header chunk at the top of each block with votes about any conflicts that have been seen. It's live and it's safe, but there's no finalization. Just doing it that way allows for the possibility that a year later Alice comes back and says, oh, and I used check number 1 to pay Dave. And so then it has to go through and decide which of those. And if someone puts 2 conflicting transactions in the same block, the validator will reject it. But any other conflicts that it sees, it has to resolve it each time. So this isn't quite what we want our system to look like. Now, the name Casanova is not the Italian lover. It is the villain from the movie Mystery Men in the late 90s. And I've got a little clip here that shows why that is the case. So Jeffrey Rush. Oh, sorry. Oh, why is it not playing through the... I can just hold... Yeah, just play it through the microphone here.
This is a fine...
One more time.
Oh, this is a fine, elegant...
All right, I'll just hold this down to it. Oh, that's not working. Alas. Okay, I'll just turn on the closed captioning and you can read along. It was prize.
Your first night of freedom, you blow up the asylum. Interesting choice. I only knew that you'd know that I knew. Did you know that? Of course.
Okay. So it's talking about who knew what, right? So, the idea of Casanova as a protocol is that we can exclude future potential conflicts if we know that enough other people know that we knew something. And that's what the complexity of the proof is about. But basically, we have all of this structure about blocks referring to previous blocks in the DAG. We assume that there's a network delay of at most delta. Now, delta is some unknown number. It's an effective number that bounds how long we have to wait before a network partition gets resolved. So, in the usual case, when everything's working correctly, it's just the transit time from one side of the network to the other. When there's a partition, the validators can continue producing blocks, but finalization won't happen until the partition is resolved, unless one side has, well, finalization won't happen on both sides until the partition is resolved. Delta is unknown, we just need it to be some finite number. So as long as the partition doesn't split the network forever, then our network will eventually get finalization. So when a validator gets two blocks with conflicting transactions, it attests to the conflict, then computes a set of witnesses for each alternative. When the validator can prove that a fault-tolerant majority of validators has seen a fault-tolerant majority of validators decide on one of the alternatives, there's no need for the consensus protocol. So if among all of the blocks and witnesses it has seen of this conflict, it sees, well, the majority of the network has already seen this one, that a fault-tolerant majority has seen this, then running the consensus protocol is useless. The outcome is a foregone conclusion. So it doesn't need to run that, and you can say that it's finalized. Now, if there is a difference of opinion, then you run the protocol long enough to reach the point where you've decided on it, and then everyone has seen everyone decide on it, or at least a fault-tolerant majority has seen a fault-tolerant majority decide on it, and so it is finalized. So at this point, we've got a protocol that is live, it's safe. If someone tries to put two conflicting transactions in the same block, they're rejected. If someone tries to submit a transaction that conflicts with a finalized transaction, it's rejected. And the only time that there's any consensus finding at all is when they're able to convince two fairly large parts of the network of two different alternatives. Now, the great thing is that with a collection of transactions in a block, we can pick out the two transactions that are conflicting and let all of the others happen. So if Alice is trying to double spend, only Alice's transactions and the ones that depend directly on hers get slowed down. And finally, the full protocol doesn't use a side consensus protocol, but is integrated directly into the protocol. When the network's partitioned, both sides can make progress. That is, you can continue producing blocks that refer to previous ones. If no one is cheating, no transactions get lost when the network gets back together. So the only time that you'll lose transactions if Alice can force the network to partition and then give different transactions to both sides, and then have enough other people spend the results of those transactions. Eventually, when the partition ends, one of those two causal chains will be rolled back. But that, we think, is a very rare case with a very powerful valid enemy. So in a part of the network where a fault-tolerant majority can form, the time to finalization for non-cheaters is 2 delta. So I issue a block that contains a transaction, you send a block back to me that acknowledges that transaction. When I get enough of those from the rest of the network, and they're sending out blocks every minute, that means it's about 2 minutes between sending a transaction in and having it be finalized. Bursty networks are slightly slower. So if on average you get 1 gigabit per second, but sometimes it's faster and sometimes it's not, then it's slightly slower, but it's still on the order of a few minutes. So I was going to have you go look at this demo on your laptops, but the local firewall doesn't allow you to hit this server for some reason. If you do it on your phone through your data plan, you'll be able to hit it. And I am actually connected via my data plan here to this thing. So this is a demonstration of Casanova-Attest running with the code for for conflict exclusion. I'm sorry, for finalization. It doesn't do conflict exclusion yet. You can see at the bottom, we've got these dashed things. These are blocks that have been issued, but haven't yet been acknowledged. The yellow bordered ones are ones that have been acknowledged, and the black bordered ones are the finalized blocks. Now, it's running at 10 times the speed, but it's telling the transactions per second as though it were running at normal speed. So with 7 validators, 7 times 83 is roughly 580. We see we're fluctuating around that. Right now it's running a bit faster. This is also a very, very bursty network. There's only a 1 in 3 or 4 chance that any block that has been produced will be received by one of the other validators during any 10-second interval. So a good network, one that has very smooth bandwidth provision, will basically look like a long helix, that everyone is getting every block from every other one before it produces its next block. And so, assuming that they are offset slightly in time according to their validator number, this one would produce one, and then this one produces one acknowledging all the rest, and this one produces one acknowledging all the previous ones. And so it ends up looking very much like a chain, but this handles even these low-quality bursty networks. So CDelta is our cryptocurrency that we are building on top of a Casanova network. So we need a notion of a conflict domain to tell when 2 transactions potentially conflict with each other in order to say these can't happen at the same time. In Bitcoin and Ethereum, because of the way multi-sig transactions occur, every transaction has the potential to conflict with every other one. So even if we used Casanova with Bitcoin's UTXO model, it would still end up being totally ordered. So our solution was to use accounts as conflict domains. We have a trie of accounts, Patricia trie, and each account contains a set of UTXOs as of a particular block number. So in a particular block, that block has a view of which UTXOs are in this account. All the inputs to a specific transaction have to come from the same account. So in Bitcoin, there's this possibility to have multi-payment, 2 different payers pay a single output. We can simulate that by having an intermediate account where Alice and Bob pay into that intermediate account, and there's a transaction that depends on those 2 transactions from Alice and Bob to pay to Charlie. There are various kinds of signature that we support. Single sig, multi-sig, this kind of intermediate account that allows you to withdraw the money, assuming that the other person hasn't put it in after a particular amount of time. Hash time lock accounts that allow you to do token swaps between different chains. And because of true finalization, you know that this really is an atomic swap rather than, a molecular swap or something that may get rolled back at some point on the other chain, you're never sure. So with true finalization, we can set up not only a single high-speed network, we can set up one in the US and one in Europe and one in Asia, and then do atomic swaps that are truly atomic between them without having to wait for the cross-the-world network times. The last criterion is that spends from an account must be totally ordered. So between accounts, we have partial ordering. Alice can pay Bob, Carol can pay Dave. There's no order between those. But when Alice pays, each one comes with a check number. Check number 1, I hand to Bob. Check number 2, she hands to Carol, and so on. A conflict occurs when Alice tries to use the same check number to pay 2 different individuals. The system maintains a map from blocks to tries of accounts containing the UTXOs. There are various kinds of transaction. There's a pay transaction, gives a particular list of UTXOs to Bob, Charlie, and say change back to Alice. That's a standard transaction, easily 90% of the transactions that occur. The problem with UTXOs is that you can chop up a big chunk of it, pay it to Bob, and then take the little bit of change left. It tends to accumulate what's called dust. And so to prevent the accumulation of dust, we have a pay all transaction type. That means take all of the UTXOs as of this block, combine them into one UTXO and pay it to this other account. So that allows us to reclaim dust very easily. The next set of transaction types involve the validators. So if a validator is bonding, they specify an account, and that money is then tracked. The account balance is tracked by every other validator in the network. Unbonding, there's a time delay to prevent the long-range attacks, as I mentioned earlier. That's roughly 3 to 6 months at this point. We haven't pinned it down. We think it'll be smaller to begin with, and then as the network grows, we'll make it longer. Rebonding. There may come a situation where, as a validator, you are running your network, your machines, and something goes wrong with your network, and you know it's going to take a while to fix it. You don't want to be bleeding out stake while you're trying to fix that. So we encourage validators to unbond, put things on hold. Nobody's expecting them to produce blocks. And then we allow them to rebond using that same stake before the 6-month delay period has ended. And bond claim, if you have unbonded and waited your time, then you can claim that. The share claim, every time you produce a block, you get a share of the block rewards. Ejection and slashing. Ejection comes when a validator hasn't been producing blocks at a fast enough rate. So when a validator stakes their bond, it starts to leak away or burn away over time. Every time they produce a block, it restores the amount that they've lost during that time. But if they're too slow, it's not quite keeping up. And if they go offline completely, then after about half the time that it takes to lose your stake, others can say, hey, you're simply not keeping up. We're going to eject you. You get to keep whatever stake is left in your account, but you're slowing the network down. You're doing more damage than good at this point. Slashing is for when a validator produces 2 blocks, neither of which is an ancestor of the other. This is an equivocation. It's actively trying to disrupt the network. And then there are some transaction types for governance. So changing the bandwidth requirements, maybe 5 years from now, a gigabit per second is so commonplace that we can easily go to 2 gigabits per second or something. We can bump those up. The block delay, are we producing it every minute, every 2 minutes, every 30 seconds? What are we doing with that? The reward size, how much do you get for producing a block, and so on. All validators keep track of each other's bond and stake. So they produce 1 block a minute, get to claim a block reward in addition to the transaction fees. Transaction fees are also distributed evenly among the network. So there's no incentive for a validator to hoard transactions. They'll broadcast them to everyone else. If a validator is topped up on their stake, all of the extra stuff that they get from the block reward and from the transaction fees goes into a wallet that they can spend immediately. So we spent a long time trying to design a system where it would make sense for someone to get into the validator business. When we started at Pyrofex, we spent around $20,000 on GPUs that's going to do some Ethereum mining. And then 2 months later, Vitalik came out and said, oh, I want to cut the block reward size in half. And all of a sudden, it was no longer profitable for us to do the mining operation. So now I've got a bunch of GPUs in my basement waiting till I have time to do a machine learning problem with them or something. But we need to have, in order to have a high quality, secure system that makes sense for people to invest in the infrastructure of this network, it has to reward the miners well. So we've designed this such that if you put the stuff as part of the network, you put your stake on there, then you will be rewarded in a way that makes sense to continue as a business. The other portion of it is the governance of the network. So there have been lots of different attempts at doing blockchain governance. There have been some really spectacular drama around many of these governance issues. I think there was Tezos, where the founders were in a fight with the foundation that was founded in Switzerland. In the Archain Cooperative, there's been some discussion about whether particular business deals were in the benefit of the chain. Lots of different problems that arise from governance. And our point of view is we already have excellent governance technology. We've been using corporations for hundreds of years. They have proved themselves to be excellent tools for doing this. So as we're offering the investment opportunity, we're offering equity in a CDelta corporation, which has the authority to govern how the software itself proceeds. Any miner who wants to be part of the network will also have an interest in having a say in how the network is governed. So they will acquire the equity in the company. And we also expect that the value of that stock will correlate with the value of the token itself. Now, we can't issue a token in advance. We'll get to SEC regulations later, so I'll put that off now. But until you are decentralized enough, the SEC says you're a security. So Bitcoin and Ethereum are sufficiently decentralized, but most tokens are not. They're controlled by a single party, and therefore we've seen more and more actions by the SEC cracking down on these sorts of things. So we've had to design our system to meet US securities laws if we want to deploy it in the US. Now, as I said earlier, we are not doing smart contracts now, but we have kept in mind the possibility of doing smart contracts once the network is successful. So we need to choose a computation model that doesn't slow down the network in the same way that we had to choose a transaction model that wouldn't slow down the network. And it turns out that the communicating event loop model that's used by browsers and Node.js and so on is an excellent fit. So that'll be very familiar and comfortable. Rather than having an account that contains UTXOs, you'll have a message box that contains messages. And then spending a UTXO in the transaction model is equivalent to processing a message here. And the result of spending a UTXO is production of more UTXOs to other accounts. The result of processing a message is putting more messages in other mailboxes. So pi calculus basically stores all of the mutable state as the value of the messages in the mailboxes. We could use that model. We could do something else where we're storing state off-chain and merely committing to it on-chain. There are lots of possibilities, but this is a sketch of how we anticipate that it'll work. Regulation and the SEC. Securities Exchange Commission has a test called the Howey test. It has 4 criteria that qualify something as a security. The only legal way that we've found to sell tokens in the United States is to sell them as part of a security, which means you have to be an accredited investor. In order to get the decentralization we need so that it's not a security at network launch, we need to have around 20 of them. Then, we look at Bitcoin and Ether, BTC.com, Ant Pool, F2 Pool via BTC, and BTC.top. Those are 5 Chinese pools that together control 51% of the Bitcoin hashing power. If the owners of those mining pools got together and decided to launch an attack, they could. Ethermine, Spark Pool have 50%, and the next 3 pools control another 28%. So roughly 5 pools in each case control enough hashing power to determine what happens on the network. And they can throw their weight around. You know, the whales that own these things can manipulate the currency and so on. So we feel that with 20, we have a pretty good defense for if the SEC looks at us to say we are at least as decentralized as these things that you've already said are sufficiently decentralized. That's the only approach that any lawyer we've talked to has said that could work. The last piece of the puzzle is how do we get people to use this thing? It may be fast and brilliant, but you know, Betamax lost out to VHS. How do we get people to use this fantastic network? Google Pay, Apple Pay, Venmo, others have already paved the way for mass adoption of mobile payments. You install an app on your phone, you go somewhere, you push a button, and they get their money at the merchant. So we're writing a software package called NumEffects. At the moment, it's an e-commerce site plugin that lets merchants get paid in crypto. We're also working with, we're working towards a point-of-sale solution so that then we can go out and sell directly to retailers and say, do you not like paying $20,000 a month to Visa for your payment processing? If you want to get rid of those fees entirely, use this, and then leave it to them to encourage their clients to do it. Say, well, they might say, anyone who pays with Visa gets a surcharge. Smith's, a grocery store chain, has stopped accepting Visa entirely. They're simply getting tired of paying all of these transaction fees to the Visa network. If we can give them an alternative, they can encourage their clients either by passing on the penalty to them or offering them discounts or something along those lines. All their clients have to do is install an app in the exact same way that they've done with all these other payment applications. So if we can get enough adoption of NumEffects, then when CDelta is ready, we simply flip a switch and all of them are able to take CDelta as well. Also, you know, when it's ready, we can also approach the exchanges, groups like Coinbase, and say, you know, here is an excellent network. We want you to support our tokens, and that drives adoption as well. So, thank you very much for your time and attention. Yes?
What are the censorship resistance properties of the validator set?
Censorship resistance in the sense of whether they accept a transaction from a client.
Correct.
Simply the fact that there are enough of them. If there are 20 different parties, you can approach any of the 20 in the local data center and send your transaction to them.
And it means to like get mined into one.
Yes. Yeah.
Second question, how do you bootstrap from Genesis for new validators?
New validators don't need to bootstrap from Genesis. They can, whenever a block has been acknowledged, when everyone knows that a block has been produced, you can archive it to tape. And so there's a very small snapshot that you can get of the blocks that have been finalized but have not yet been universally acknowledged to be universally acknowledged, the ones that haven't yet been archived. That small snapshot is something you can send them immediately. The question of the integrity of that snapshot is one that you have to answer when you are starting to join the network in any case, right? How do you know what the Bitcoin Genesis block is? Well, it's published on lots of websites, you've seen it. In this case, the IP addresses of the validators that have bonded are also widely published, and so you can trust that over the specific Genesis block. You simply trust this is an authoritative list of servers where I can get the current state.
How would one register for that list if they wanted to run their
You acquire tokens from someone who already has them. You know, pay them, get it somehow either on an exchange or personal deal. Then you send a bond transaction to the network as a client that says, here is the the bond, here is my public key as a validator. Once that gets accepted, you're in and you can vote. Yes?
That there was a type of transaction that picked up dust. I was just wondering, what is the dust that was mentioned?
So say I've got 10 $1 UTXOs. So the question was, how does dust form? If I have 10 UTXOs for $1, and I'm making 75-cent payments, right? I've got quarters left over. None of those UTXOs themselves are sufficient. So then I have to start bundling UTXOs. If I'm doing something where it's paying 99 7/8% of a UTXO, you get these little bits that aren't even enough to pay the transaction fees anymore. And so it doesn't make sense to assemble all of these things into a big payment that mentions them all by name, because it just becomes too expensive to spend them. And that's the dust problem. So if you've got a whole bunch of these microscopic valued UTXOs, then you can do a pay all, and that's a short way of bundling them all together that's cheap enough to make it worthwhile.